Welcome to our technology session. This session is going to be presented by Karen Camp, who's just amazing, and she is presenting What Do You Notice? Strategies for Inquiry with TI-84 Technology. So I'm going to hand the ball off to Karen in just a minute, and we'll hear from her.
Excellent. So glad to be here today, Ray, and so glad to be speaking with all of you about What Do You Notice? Strategies for Inquiry with Technology. I'm Karen Camp. I'm a T³ National Instructor from Connecticut. You can reach me at karen.camp@gmail.com or on Twitter with the handle @KarenCamp. At the end of the recording, I will give you the link to the Dropbox with all of the materials that I'm going to go through today, the handout, and all sorts of student activities. So strategies for inquiry are things that we can do as teachers to enable students to use critical thinking to build understanding of math topics. These techniques provide entry points into problem solving, encouraging engagement and sense making, and they can also make the math learning deeper and more durable. The 4 strategies that we're going to cover today: noticing and wondering, which one doesn't belong, action, consequence, reflection strategies, and the last one is same and different, or compare and contrast. So first, what do you notice? What do you wonder? This strategy has us getting students involved in a mathematical context before being asked to do something with it. The way you do this is present a graph, equation, or problem scenario and give students individual think time to note down what they notice and wonder about the context. Then discuss and elaborate important math concepts. I want to tell you that the handout has resources besides my own resources to read more about this on the internet. Most of these strategies are nothing that I have invented. I'm just sharing them with you. And so you can find other sources for more ideas beyond the ones that are in our Dropbox. Today, we're going to have about 12 examples we're going to go through. And let's dive into our first one. First example is on your calculator, graphing x squared, x to the 4th, x to the 6th, and what do you observe? The second part of that is we're going to graph the odd numbered functions. Those of you who teach Algebra 2, pre-calculus, doing end behavior, that was the goal of this lesson. And one of the things I want to tell you about noticing and wondering is that sometimes students will notice mathematical features of the situation that aren't part of what you intended to teach. And I want to tell you that sometimes taking the scenic route towards the math you wanted to learn will open up some really rich discussions. And by the way, it's totally okay to park an idea that a student has if you don't want to deal with it at that moment. But once I took this lesson and did it in a notice and wonder format, we had really wonderful conversations. So we're going to go to our TI-84 SmartView emulator, and let's take a look at x squared, x to the 4th, and x to the 6th. And this SmartView emulator projects the calculator to the class. It's a 90-day free trial if you want to download it from the Texas Instruments website. And let's just take a quick look at what our window is set at. I'm on our standard window. And when we look at the graph, we can take a quick look. What I like to do with the color versions of the Texas Instruments 84 plus family calculators is I like to do a lined grid because it helps students pay close attention to some features of the graph. So in order to show that grid, I'm going to go to a second format, and I'm going to go down to grid line, and let's relook at the graph. And by the way, I don't prefer to show a grid on the black and white versions of the calculator because there's only a dot grid and it tends to be more distracting. But on the color versions, it really enhances the student experience. Take a look at my graph grid and just think about the grid itself. What do you notice about that grid? And I'm hoping that you notice that the scaling on the x-axis has different sizing than the y-axis. So we're not getting a square window, if you will. If you're teaching Algebra 1 and you're talking about slope, you might want to have students counting boxes up and to the right or down and to the right. And having a square grid really enhances the student experience. So let's change the window to my favorite window, which is the Zoom decimal window. And what Zoom decimal does is it makes a square window, first of all. It also, when you trace on the Zoom decimal window, it's going to trace by a tenth of a unit. The pixels are equalized to the number of units. So your trace values are really lovely trace values. And later on, we'll see some other fun things that the Zoom decimal window helps us enhance. But let's stop our tracing and just looking at the graph. And what do you notice? What do you wonder about these three graphs? And hopefully that you observe here that the three graphs, the blue one is x squared. And by the way, when you're tracing, you can have the function definition shows up here. And then the blue one arrow down to the red one tells us that's x to the fourth. And the black one is x to the sixth. You can see that the blue one, as we go from blue to red to black, they become steeper over here. And students also notice that they become flatter over here. Students might notice that they have common points, -1, 1, +1, 1, and 0, 0. And what we can do is we can investigate what happens when we zoom in on the graph or look at the values numerically in a table. I'm going to zoom in. When you hit the zoom menu, one of the choices is zoom in. A cursor will appear wherever you want. It normally appears at 0, 0 if you haven't moved the cursor lately. But that cursor is going to be the center of your zooming. And when you hit enter the second time, it will zoom in to a certain factor, and you can adjust these factors. And so students who wanted to pay attention to the flatness of these lines, notice that the order that they flatten in is opposite order that they're becoming steeper in. So the blue one, the x squared, was the one that was the least steep. I guess actually it's the least steep and the least flat. So as you raise the exponent, it becomes flatter in this area. Let's also take a look at this numerically with a table. The second window, second table set allows us to set up our table. I'll start at 0 and we'll increment the table by 1. And when we take a look at this, we can see what's happening with our steepness. For a given value, let's say x equals 4, we're going to go from 16 if we're x squared, 256 if we're x to the fourth, and 4096 x to the sixth power. So clearly that's where we're getting the steepness in. Let's move back up to 0, and let's go back to table set. And now, actually, excuse me, we didn't have to go back to table set to change our increment. This is what I wanted to show you. When we're in our table, up here it says press plus for delta table. And just pressing plus allows us to change our table increment right from inside the table. And if I enter there, now we're going to be incrementing on 0, from 0 to 1 by a tenth. And let's take a look at these values. The blue value for x equals 0.5 is 0.25, or 2,500. If you can imagine, there are two more zeros in the next two decimal places. 2,500 10,000ths. The red graph, the y to the fourth, is 625 10,000ths. And the black graph, y to the sixth, x to the sixth, is 156 10,000ths. So numerically, we can also see these values flattening. So what I love about this is it gives students an opportunity to examine the graphs visually as a graph, and also gives them an opportunity to examine it numerically. And by switching up the multiple representations and giving students different entry points into the situation, they're getting a lot more deeper learning. Of course, the rest of the activity was to take a look at what happens if we go to x to the third and x to the fifth and x to the seventh, and how are these odd powers the same and different? How are these different and the same as the even powers? Let's go back to our Zoom decimal window. And you can see the same steepness and flatness happening and examine that, but you'll also see my original intention for the activity, which was end behavior, that these three odd powered functions are going to be starting low and ending high. with different end behavior than the even-powered function. Moving right along to our second activity, let's take a look at some quadratics and a rational function. So y equals 2x squared minus 8 and y equals x squared minus 16. And what I want you to think about, even before we get graphing on this, what would your students notice about these equations? Hopefully you can see we've got quadratics. These will be in the shape of a parabola. And perhaps your students will notice that we're going to have some low y-intercepts. So our zoom decimal window is not going to be all of that useful for us. I like to have students thinking about what window would be appropriate and have them develop that for themselves. What I also want to show you is that there's a feature in the Zoom menu called memory. And when you go to Zoom memory, you can store a particular window and recall it later. And I've done that for this. And so our Zoom recall gives us a more appropriate window. I've kept my X domain to be the same as the Zoom decimal window, which enables us to still have those tracing nice trace values, the X increment. Okay, so what do you notice? What do you wonder? Let's take a look at the rational function. The rational function is a fraction. We could do parentheses and a slash, a division slash, to represent this rational function, but one of my favorite features of the TI-84 family is the fraction template. On the CE model with the newest operating system, if you press alpha X, you're going to get this fraction template. On all other models, press alpha Y equals to get the fraction tools and choose the numerator over denominator template. The template enables students to input the math into their technology in the same notation that they're looking at it on their papers. And that is going to have them reduce the number of errors and really be able to examine the situation. The other thing we can do here is you can have students retype these functions, but retyping also makes them susceptible to errors. So let's use the y variables. They are in alpha trace. Here is our y1, and that's going to go in our numerator, and we want to divide it by y2. We put that in our denominator. And let's take a look at the graph. And what do you notice? What do you wonder? I would hope that students observe things like the zeros of our y1 are here, and notice those are also the zeros of the rational function. The zeros of y2 happen to be the asymptotes of the rational function. The asymptotes, you can, excuse me, it's in under the Zoom format menu. You can have it detecting asymptotes, which means it's not going to try and connect the graph. It's going to make it with literally an unconnected graph. But the zeros of the denominator function are the asymptotes. And the other thing I want students to think about and notice is the y-intercepts. What's the y-intercept of the blue function, the numerator function? What's the y-intercept of the red function? -8, -16. And what's the y-intercept of their quotient, the rational function? It's 1/2. This kind of a picture, this kind of a graphical view really helped my students get a deeper understanding of rational functions beyond just algebraic manipulations. Can you factor the numerator? Can you factor the denominator? Can you find their zeros? Moving along, our next strategy is called Which One Doesn't Belong? Students generate a reason why one of 4 choices doesn't belong and justify why their choice is valid. The way you do this is you present 4 items to students. They could be graphs, equations, shapes, numbers, and give students individual think time to note down what they think doesn't belong and why, and discuss why each of the items might not belong. There's many examples of which one doesn't belong on the internet, and there's an entire website, wodb.ca. And so just take a quick minute, take a look at these 4 graphs of linear equations, of equations of lines, and think about what you think doesn't belong and think of a reason. Now, there's more than one right answer. The idea here is that a well-constructed which one doesn't belong will have good reasons why each of the 4 options doesn't belong with the other 3. So for example, you could say the lower right here is the only one with a negative slope. The lower left is the only one with negative y-intercept. The upper right is the only one that goes through the origin. The upper left, it's the only one that, well, looks like it's the only one with a slope of +1. Looks like it's going up and to the right by the same amount. Now maybe it's, yeah, so it looks like it's the only one with a +1 slope. And there's more than one right answer, and you want to generate discussion. By the way, you've heard me talk more than once already about individual think time. It's really important to give students time to think themselves about what they think before going to partner or group work. The other thing that you can do, a tip I've learned, is if you do want students to discuss with their partners, you can give one device to 2 students. And that way, one student is pushing the buttons or moving the mouse, and then the other student is helping record, and they're discussing. When you give an individual device to every individual student, there's less discussion. So a way to promote discussion is to share a device between 2 students. Here's our next example, which one doesn't belong with quadratic functions. These functions we're going to take a look at on the calculator in a minute. Think about what one you think doesn't belong and give a reason for your choice. And these are screenshots, and I'll show you how to take a screenshot to get 4 separate ones. What I'm going to do here is I have these already loaded in a different part of the TI-84 SmartView emulator. This emulator is 3 emulators in one. It's the CE, the newest model of the calculator, the TI-84 Plus C, as well as the TI-84 Plus black and white model. The C and the CE are almost indistinguishable to students. So if I have a lot to do in a class, I might load some things up in the C. Here are the 4 functions that those 4 screenshots came from. You'll notice that only the first y1 has its equal sign highlighted. That means that that's the active function. So here is the graph. If you want to take a screenshot, you hit this camera icon up here, click on that, and then you can save it, you can copy it, put it in a test or in a worksheet for students. So there's lots of things that you can do with that screenshot. Okay, let's go back to our y equals screen, and I'm going to press enter on each of these equal signs to activate them all so we can look at them all together. And which one doesn't belong? You can say that the blue one doesn't belong because it's the only one with a positive leading coefficient. Or perhaps your students aren't even to that stage. Maybe they're just going to say this is the only one that opens up. Great noticing, and you can then talk about how opening up and opening down means the equations will have positive and negative leading coefficients, or students can discover this information for themselves. I like to actually introduce the terminology of concave up with Algebra 1 and Algebra 2 students so that later on that terminology meshes with what they're going to hear in calculus. Anyway, the blue one is the only one with a positive leading coefficient. The red one is the only one maybe that goes through 0, 0, or you could say it's the only one that has a different line of symmetry than the other 3 because these 3 have the same line of symmetry. The black one is the only one that has its vertex off of the x-axis, and the pink one is skinnier than the rest. And yes, we're going to have students eventually understand that that skinniness has to do with having a leading coefficient that isn't 1 or -1. Okay, the next, which one doesn't belong? This one I got off the internet, and it, on the face of it, just is giving us 4 sort of classic functions in our function library: log x, 1 over x, absolute value of x, and floor of x, or the greatest integer function. And again, I like to have students experience this graphically. So let's take a look here at what they look like graphically. So log x is here. The next one is going to be 1 over x, which I could put in using my fraction template. The fraction template on the C version of calculator is under the alpha y equals. So I could do that, but when you use a fraction template, it's going to force certain answers into a fraction form. And I want to look at these later in a table. So I want to get a decimal answer. I can change my mode up here. It says the mode is auto. So it's going to automatically send fractional answers to fractions. I could change to decimal, but I don't want to change all my mode. I'm just going to use x to the -1 power to represent that 1 over x. The next one is the absolute value of x. Alpha window has some of our function shortcuts. Many of these are already in the math menu, but they're here, alpha window, if you want them. So here's absolute value of x. And then y4 is going to be the greatest integer function, which is in the math menu under num, and it's the number 5, the greatest integer function. And let's take a look at the graph. And here I like to have students thinking about what do you know, which one doesn't belong based on a variety of things. They might be interested in domain and range here. So the blue one, log x, is the only one that doesn't have negative values in its domain. The absolute value of x is the only one that has a continuous function. There are no breaks or jumps. The reciprocal function 1 over x is one of the ones that doesn't have x cannot equal 0. And I know it can't equal 0 on the log x either. But a step function is the only one whose outputs are integers and can't be decimals. And the step function is also the only one that is discontinuous within its domain, that it has jumps even though it is defined all along the domain. Okay, the which one doesn't belong isn't limited to algebra. There are plenty of numerical expressions that you can work with students. This one here is one that Algebra 1 students might see, but Algebra 2 students might see. And you can do this on the home screen. I just like to show students all the different ways that they can find the square root of 16. So square root of 16 is here. We can also do 16 raised to the fraction template 1/2 power. Okay. The next, which one doesn't belong here, is a decimal one. This is actually great for middle school and high school because even our high school kids aren't necessarily sure what all these different values mean. Only the upper left has a different value. 0.3 repeating is a different numerical value than the others, but these are different ways of representing it. And so having a discussion about different representations of the same number and how they may or may not be confusing and what they're used for is a really good example. And my last which one doesn't belong example came up when I was working with a student using different log and exponential functions. One of the things we have to be careful as teachers is when we have fantastic technology, we also have to make sure we know what the technology can and can't do. I want my students to be able to figure out what log base 2 of 16 is without a calculator. So we're going to make sure that they have that skill. But when you're trying to pay attention to comparing 4 items, you may want to give them the calculator. Alpha window, there is a log base function on your TI-84 calculator. So that means that if you're teaching change of base, or this is a log function that students should be able to do without a calculator, you need to test and practice with and without technology. So if this is a skill you want students to do without technology, make sure you have part of your quiz, part of your test that is done without technology. Anyway, log base 2 of 16 is 4. log base 16 of 4 is a half, or 0.5. There was one that was 8 to the x equals 16. And in order to solve 8 to the x equals 16, I might have my students using common bases and doing this without a calculator, but they could also convert it to log form. So it's log base 8 of 16. By the way, you can arrow up in your history and press enter to pull something down so you can edit it. And what that does is it gives you an opportunity to not type things over. So log base 8 of 16 is going to be 1.333. And the last one was log of 16. And we know that log of 16 is base 10. And remember that log is asking kids, what power do we need on the base to get this number? So you can ask students, what do you think? Do you think that the 10 or the 8 needs a higher power to reach 16? And hopefully they say that the 8 needs a higher power because the 16 needs a lower power. Okay, moving right along, we have our next inquiry strategy is action, consequence, reflection activities. These types of experiences have students performing a mathematical action, observing a mathematical consequence, and then reflecting on the result and reasoning about the underlying math concepts. The questions that you ask students when they observe the consequence can be very simple. What did you observe? What changes? What stays the same? And this reflection piece has turned out, I have discovered myself, is really the critical piece of the whole activity. I had experiences where I did a great lesson with technology and students did the lesson, we experienced it with the calculators, and they came away from it learning, I thought learning what I wanted them to learn, but a week or 2 weeks later, they only remembered that we did something on the calculators. They couldn't remember what the math was that I had wanted them to learn. So a really important point is you have to give students the opportunity to reflect. You have to give them the opportunity to discuss. And especially important is to summarize for the class, either by the teacher or by students, so that the important mathematical learnings are not lost. So we do this by engaging students with graphs, sliders, dynamic tables, or searching for invariants. These are 3 different categories of action, consequence, reflection activities that we're going to see today. Require your students to record their observations. Don't just view the math, do the math. I provide students with a lab sheet for them to write down what they see. Their sketches don't have to be perfect, but they have to note down what they think is important. Ask the students to make predictions, discuss conclusions, and as I've said, summarizing with the class is really critical. Some of you may have heard that, exploration math or discovery learning, it gets a little bit of a bad rap because people think that students don't learn what you want them to learn. This summary piece, making sure that your math objectives were covered, making sure that students don't come away with misconceptions, that's the key piece. And that's the reflection piece and summarizing with the class. So asking good questions will enable students to reflect and consolidate their learning. You can say, what will happen if I do this, if I change the exponent? What must I change to make something happen? How is one thing affected by another thing? What changes? What stays the same? When will something be true? And why does this happen? Our first 2 examples of action, consequence, reflection activities are with graphs and sliders. And for that, we're going to use the transformation graphing app that is built into all of the calculators. We're going to return back to the 84 plus CE. And I'm just going to clear all this stuff out of y equals. And we're going to hit the apps button, and transform is at the bottom. I'm going to arrow up to get to it quickly. And looks like nothing has happened. Didn't really see any difference on this screen, but when you go to your graphing screen, first of all, on the color calculators, it tells you that you're in transformation graphing. And you also see these here. These are little play pause icons. If your calculator, when you do this, shows 2 play pause icons and the rest normal down here, that means you have the most up-to-date version of transformation graphing. If you show the play pause icons all the way down, then please do update your operating system to get the most out of your calculator tools. The transformation graphing app allows you to have 2 different transformable functions here, and you can also graph other functions. Prior versions were a little bit more limited. Okay, so let's first talk about the standard form of a quadratic, and we're going to do ax squared plus bx plus c. What I like to do is I like to make that multiplication explicit for students, because with all the letters going on, sometimes they're not paying as close attention as they should to what math is happening between a and x squared, for example. The other thing you should know about transformation graphing, it lets you set 4 different parameters, a, b, c, and d. So for quadratic functions here, a, b, and c are part of those. If you wanted to do slope of a line, y equals mx plus b, you have to use a different letter than m because m isn't one of the transformable parameters. The other thing about transformation graphing, we can change our window, but in window, we've got an arrow up to the window settings. And so you can leave a trail if you want. You can set where your parameters start. I'm going to leave them as they are here. A is 2, B is 1, C is 1 with a step size 1. And this thing that's flashing at us is just going to be a play pause icon, which means as I make a change, it's going to show it to me and then it's going to wait for new information. These other ones allow you to sort of watch something as it does it automatically. I prefer to do the play pause. Let's zoom back to our zoom decimal window. And here is our quadratic function. A equals 2. The way you change a parameter is the right and left arrow. Up and down switches from one parameter to another. So you increase by hitting the right arrow. So what's happening as A increases, we're getting skinnier. What's happening as A decreases, we're getting a little bit wider. What happens if A is 0? Ooh, what's that? Wonder why that happens. Here's our negative values. Okay, now I'm going to arrow down to get to the B parameter. And actually, before I even get to the B parameter, let's go back to the A parameter. I'm going to make A 2 again. If I want to examine more closely, if I want to change my increment, I could do it here. Actually, I'm going to save that for our next example. Let's go down to B, like I said, and let's see what happens when I change B. B is a very interesting thing. A lot of courses don't really cover what B does, but watch your vertex as I'm changing B. Where's the vertex going? Turns out that as B changes, the vertex moves in a parabolic fashion, which is really kind of neat. I can also jump to a new value. So if I want B to become 1 again, while the B parameter is highlighted, I just press a 1 and hit enter, and I'm going to jump back to the 1. Let's arrow down to C, and as we increase C, our y-intercept increases. As we decrease C, our y-intercept decreases. And one of the fun things you can do with this is you can have students do a match my graph. If you have a smartboard that freezes so students can't see what you're doing, you can jump back to the y equals screen and type in a new function. I'm going to type in negative x squared minus 2x plus 3. I wouldn't show this to students if I want them to match the graph. But my job is to change my parameters to get this matched. So first of all, I'm going to, looks like my graph is a little bit skinnier. The blue one is a little bit skinnier than the black one, and maybe I've learned that increasing A makes it skinnier, decreasing A makes it wider. I also realize that this has to be concave down or opening down, so I want a negative value. That looks good. Maybe I want to change my C value. I need my y-intercept to be higher. And now let's go and change the B value. And students can work with this until they've matched the graph. Really fun. Our second transformation graphing example is going to be the exponential function a to the x. And let's go to the graph. Whoops. I left a in a negative value, so that's a pretty fun, interesting graph. It's not continuous. Let's increase a to where I wanted it to be, which was 2. And so what happens with 2 to the x? What happens if it goes to 3 to the x, 4 to the x, 5 to the x? What do you notice? What stays the same? What changes? Students might notice that this y-intercept doesn't change, but that the graph gets steeper here and flatter here. What happens if a equals 1 or 0? Here's a equals 1. That's a line. 1 to the x. Here's 0 to the x, which is still a line but has a different domain. If I want to change my increment for my parameters, I could go back to the window settings, but notice this setup right here. That's right above my graph button. If I hit graph, I jump right to my settings, and I can change my step size. And so we can take a look at what happens if we go through our base stepping by 0.1. There's 2.1, 2.2, 2.3, 2.4. You can maybe estimate E if you like. Okay, so graphs and sliders is one category of action consequence reflection activities. The next kind is invariants. And invariants are parts of a mathematical situation that remain the same even as others are changing. These can be numerical invariants where certain quantities or sums of other quantities remain the same, or it can be locations or parts of a geometric figure or things like that. So I've got 2 examples to share with you. One of them is circle angles. We're going to go to our apps again. Oh, excuse me, let me get back out of transformation graphing. In transformation graphing in the color calculators, along the top of the screen, there is a quit app option so that you quit transformation graphing. In the black and white calculator, it's a little bit different, and there are handouts in your Dropbox file that you will get later that explains how to exit transformation graphing on the black and white calculators. Speaking of the black and white calculators, Cabri Jr. is a geometry app. And the difference between the app in the color and the black and white is more than just color. The color calculators have a greater pixel density, and so some of your figures won't look the same if you try to use a file from the color to the black and white, or it won't work at all. So in your Dropbox folder, there are black and white calculator files for these activities as well as color. So keep that distinction in mind if you're going to use the pre-made activities. A pre-made figure allows students not to worry about the construction aspects of it and to focus in on the math we're trying to teach them. Of course, if you wanted to investigate these deeply in a geometry class, you could have students constructing them themselves. In Cabri Jr., the graphing keys, y equals, window, zoom, trace, and graph, are the keys that give us our menu. Here's the y equals key. Our window button gives us our objects. The zoom button gives us construction tools. The trace button is transformations tools. And the graph button is measurement, hide and show, and other things. In y equals, we're going to open up our circle angle figure. And actually, before I even open that up, I want to show you what students start with. They start with a lab sheet for them to note down their work or their observations and their conclusions. And notice that the beginning of the lab sheet doesn't have any of the angle measures that I had up on the calculator. So I want students, when they first look at this, is to write down some things that they notice. I want them to notice things like A, B, and C are on the circle itself, on the edges. So you might call BC and AB are chords, AO and CO are radii. Getting at the idea of what makes a central angle, what makes an inscribed angle, but students might notice that angle ABC is acute and maybe angle AOC in this picture looks like it's perhaps a right angle. That's okay if they notice those things that are off of what I was looking for, but this part of my worksheet make certain that students have the definitions before they carry on. Because if the object of this lesson is to have students knowing how to calculate inscribed and central angles, they need to know what is a central angle, what is an inscribed angle. Um, so what we're going to do is the lab sheet uh, points students to move the cursor around and grab and move a particular point. Make a conjecture, move C to several locations to test your conjecture. So what we're going to do in File here, you use the arrow keys to move your cursor. And when you are about to grab something in a dynamic geometry setting, you want to make sure you're grabbing the correct thing. And every dynamic geometry program, TI-Inspire, for example, or this Cabri Jr. on TI-84, there's some sort of indicator that you're grabbing the right thing. First of all, my cursor has become a hollow arrow, but you can see it's pointing to the letter C. So if I grab it right now, it's going to move the label. I want to move the point. That flashing circle means I'm going to be grabbing the circle. I don't want to do that. Here I am. My point is flashing. So now I know I'm grabbing the right thing. And the grab key is the alpha button. Now I can move point C around. And what do I notice? Looks like perhaps the angle B, the inscribed angle, is half of the central angle, or you could say the central angle is double the inscribed angle. Every dynamic geometry setup, you want to have students drag and observe, make changes, see what changes, see what stays the same. If students have the conjecture that the central angle is going to be twice the inscribed angle, let's test it out by doing some numerical math. I hit clear to let go of my grabber hand. And up here in the corner, I have text about the ratio of AOC, the central angle, divided by ABC. Now, I could have students divide either doing it in their head or on paper or on the calculator, on a calculator. We're not on the calculator screen right now, but we can also have the Cabri Jr. doing that division for them. And I've already done it and it's hidden here. If you press the graph button, there's a hide show tool. And the hide show tool is a toggle. So if it points to something that you are currently showing, it will hide it. If you're pointing at something that's currently hidden, it will show it. The only thing I can say is that it doesn't immediately show you where the hidden things are, so you have to remember where you hid them. And I hid this division underneath those words, and when I get my cursor there, I can it gives me a little highlighted box, and if I hit enter, now it is shown, and that ratio is going to be 2.0. What is really nice about this, the way that this is set up, what happens if you move point B? Point B moving might be a surprise to some students because grabbing point B and moving it doesn't actually change either angle. If we go back to point C, the angle measures change again. And you'll notice that my ratio, my calculated ratio, doesn't change even though the other features of this diagram are changing. Back to the student worksheet. What do you notice? Write down some observations. It also finishes up with asking students to describe the relationship, and perhaps you want to have them prove the relationship. The second action consequence reflection activity in the category of invariance is a classic one on interior and exterior angles of triangles. And here we've got all three angles of the triangle, the interior angles measured, as well as the exterior. I also have all the sums that I want calculated. We could hide them if we wanted to, the way I did it with the other ones, and so have students show those if you want them to do it. Because again, we want students to experience this and come up with their own conjectures. So if we move point B, what changes, what stays the same? What happens if we create a right triangle? Let's see if the pixels will let me. There's a right triangle. What happens if we create an obtuse triangle, etc.? Lots of things you can do with this. And just to show you the lab sheet for that one, students are going to, what do you notice? Take down some data. What happens when you add other pairs of angles together? There's also an extension. List the measures of the exterior angles of your triangle, one at each vertex. I originally made this extension because I had students working at all different rates in my classroom, and I wanted to have something for fast finishers to explore. And finally, make predictions, apply what you've learned, and if you wanted to do it in your curriculum, prove one of the conclusions from the activities. The third type of action consequence reflection activity is dynamic tables. I never really thought about the table on the calculator as being something that I could dynamically interact with. But when you normally work with tables, your independent and your dependent variables on your table are automatically filled in. So the table just gets filled in. I played around with that and discovered that if you change how you set this, set the independent to automatic, for example, and dependent to ask, you can fill in a column one at a time and ask students how the function is changing. So we're going to examine a linear and an exponential function. Back at our calculator, we do second quit to get out of Cabri Jr. I'm going to do 2x as my linear function in y1 and 2 to the x in y2. And under table set, let's start at 0 and increment by 1. And let's set our dependent variable to ask. We could, of course, take a look at these on the graph, have students see how they differ on the graph. But this focuses on the table. What happens when we fill in the y values for y1 equals 2x? Press enter and then the down arrow. We go from 0 to 2 to 4, 6. And you can see that this function is growing by adding 2 each time, for each change of 1 in the y value. Students may say it goes up by 2. I suggest that you have them be precise in their mathematical language, that you add 2 each time. In the exponential function, 2 to the x, what happens? How does this function grow? We are multiplying by 2 each time. Now, you don't have to do this in order. You could jump down here and find any value you want. What this does is it gives students an opportunity to dynamically see how an equation is growing and how exponential and linear growth are different. Okay, the second part of this dynamic tables is you can also ask students to model when one scenario catches up with the other. In this case, we're going to set the independent to ask and the dependent to auto. So this time the table is going to fill in one row at a time. So we have two scenarios. You start with $100 and save $5 each week, or you start with $5 and each week save double the amount that you saved the previous week. So if we're starting with $100 and saving $5 each week, that means in the second week, at time 0, when everything has begun, I will have $100. At the end of week 1, I will have 100 plus $5. At the end of week 2, I'll have 100 plus 5 plus 5, or 2 5s, So 110. At the end of week 3, I'll have 100 plus 3 5s. That, what I just talked through, is how I develop the idea of building that linear function. It's going to be 100 plus 5 times the number of weeks. The second scenario, where I start with 5 and then I double it, it's 5 times 2 to the number of weeks, because after 1 week, it's going to be 5 times 2, but after 2 weeks, it's going to be 5 times 2 times 2. After 3 weeks, 5 times 2 times 2 times 3 for an exponent of 3. Okay, so let's go back to our table. I want to start with 0, increment by 1 week at a time, but this time we're going to make the ask be independent. Let's take a look. If we have week 0 before we start, we've got starting with $100 or $5. Week 1, week 2, week 3. Looks like the first scenario really has a ton more money, but once we get to week 4, we can see that the second scenario catches up and goes past. Now, weeks are sort of a discrete item, so you could talk about whether it happens on the 4th day or the 3rd day of the week, but it's somewhere between week 4 and week 5. But this way of using dynamic tables allows students to model situations and see how everything fills in 1 week at a time. Okay, our fourth inquiry strategy, we have just a few more minutes left. Our fourth strategy is called same and difference, or compare and contrast. In this strategy, you ask students to compare and contrast features of 2 mathematical situations. It's really powerful when students must choose a solution strategy. So if you are teaching methods of solving systems of linear equations, or you're talking about different forms of the quadratic equation, you might want to have students compare and contrast which method is good to let students choose that. But in any case, present 2 math situations, have students examine and note how they are the same and how they are different. And our last 2 examples for the day, one of them is another one with quadratics and rational functions, x squared plus 6x plus 8. So let's go back here. Let's clear this out. X squared plus 6x plus 8. You're all math teachers. Can you put on your Algebra 1 hats and factor that? In our y2, I want to put x squared plus 6x plus 8 divided by x plus 2. Okay, and compare and contrast these. Wow, these are very different. One's a parabola, one's a line. You might notice that there's a hole in the line. Oh, that's pretty fabulous. That hole, by the way, is a consequence of using the Zoom decimal window with its equalized pixels. If we go back to Zoom standard, you can't see the hole. You can trace to the hole. Remember, the trace increments on Zoom standard don't work so well, but if I know where the hole is, I can enter the value and I can jump to the hole on a trace, but I can't visually see it. It does show me that there's an undefined y value, but Zoom decimal really is pretty amazing because my traces right to where I want to go. Oops, I'm somewhere else. There we go. Up and down arrows and trace switch functions, and left and right moves you along the x-axis. So here I can trace straight to the hole, and you can see that cursor disappear. Anyway, in terms of what you can compare and contrast, these 2 functions do have the same x-intercept over here, so that's kind of neat. Back over here to our factoring, I think that all of you might have factored that numerator to x plus 2 times x plus 4. And what I want to do right now is I want to turn off my quadratic. And I also want to show you what another great feature is graphing styles. And you can, on all of the calculators, change the line style. On the color calculators, you can change the color of your graph. But on all of them, if you arrow all the way to the left, you can change your style from a line to inequality, shading above the graph, below the graph. This is the one we're going to use. It's a tracer ball that leaves a trace behind. This one's just a ball that moves along a function without leaving a trace behind. Then there's dashed graphs, thin, and back to normal. Here's our tracer ball. arrow to the OK and press enter. And so let's take a look at our rational function and the simplified version. The tracer ball moves a little bit more slowly, which enables students to see that it fills the hole. It is the same graph, but their domains are different. Another way to take a look at this is to take a look at the table. My table is set differently than it was before. Let's put it back to auto. And let's do this. Okay, you can see that my rational function has an error or an undefined value here at x equals -2, while the linear function has a value. Okay, the very last example, I know we're running out of time. Compare and contrast. What if we wanted to take a look at exponential functions? If I wanted to take a look at 2 to the x versus 1/2 to the x, I'm going to put parentheses around my fractional base. I have my students put parentheses around the fractional bases and negative bases as a grouping symbol. And what do you notice about those two? Compare and contrast. Hopefully students notice they have the same y-intercept. They actually have the same shape. They're just reflections of each other. And many students don't realize that, or they don't realize initially, that 2 to the negative x power is the same as 1/2 to the x. There's our tracer ball to trace over it. You can use the tracer ball for factoring as well. You can have students enter a quadratic into y1 and then enter the factored form with a tracer ball into y2 and see if it traces it out. Finally, my very last example here is going to be using a log. And let's compare and contrast 2 to the x and log base 2 of x. And how are these the same? How are they different? What do you notice? There is a line of symmetry. The y equals x line of symmetry. And since we're on our zoom decimal window where the x scaling and the y scaling is equalized, you can actually see that symmetry very nicely. If you were stuck on a standard window, it doesn't quite look as symmetric. So that's why I love the zoom decimal window. So I know that that was a really chock full session. Here is the information you need to contact me, karen.camp@gmail.com. At Karen Camp. I blog at Reflections and Tangents is the name of the blog. Hang on, I've got it right here just to show it to you. Oops. Here's the Reflections and Tangents blog at karendcamp.wordpress.com. And the Dropbox folder where all of the materials for this session are housed is at bit.ly/inquiry strategies, uppercase I, uppercase S. It was my pleasure to be here today sharing inquiry strategies with you, and I hope that you and your students can use these to make your math learning more durable and more long-lasting. Thank you so much. And Ray, let me give you back the ball for our wrap up.
Thank you so much, Karen. That was awesome. I just have a few more slides for participants to help them with some resources for you. So let me just share my screen with you here and show you what some of those resources are. If you would like to think about what you learned and to compare notes with what others have learned from this conference, here are some hashtags that will help you to share with others what you've learned and to see what others have learned at this conference.
Ray, do you have it up yet? I don't see it.
Oh, yeah, it says I'm sharing, but just a minute. Let me try that.
While he's getting that up, I want everyone to know that there's a robust online math learning community on Twitter. The hashtag T3Learns is a great way to get in touch with other folks using TI calculators. And a lot of what I've learned from the online math community.
Awesome. So here's that hashtag that Karen mentioned, T3Learns. Also the one for the conference in general, T3IC. And then if you would like, a certificate of attendance for this session, you can download it at this website, https, it's a bit.ly website, 2W1RB7W, and you'll get a certificate for this particular, for Karen's session.
Well, thank you so much for having me here today, Ray, and happy Pi Day to you all.
Thank you so much, Karen. Take care.